Good morning to all. Today we are going to determine the band gap of a semiconductor thermistor using post office box. Apparatuses: post office box, galvanometer, battery, we have a beaker and then test tube, thermometer and thermistor. We are going to determine the band gap of this semiconductor, which is taken in the form of a thermistor. Thermistor means thermal resistor. When temperature increases, its resistivity decreases. The connections are the galvanometer, which is connected with a G in the post office box, and then B, which is connected with the battery. This is the B, which is connected with the battery, and then X, which is the unknown resistance, which is connected with the thermistor. The band gap of a semiconductor formula is given as Eg is equal to 2K into dy by dx. K is the Boltzmann constant and dy by dx, which is obtained from the slope value of the graph, which is plotted between the resistance and the temperature. This is the tabulation for the band gap of a semiconductor. Temperature degrees Celsius, and that temperature it is converted to Kelvin. P and Q, which is the fixed resistance, which is 1000, and S is the variable resistance, R is the unknown resistance, and from that R we are calculating ln R and 1 by T, which is for the Kelvin inverse. So for Kelvin temperature we have to calculate 1 by T. For the room temperature 27 degrees Celsius, so we are going to measure the resistance S value and R value, which is same as the S. We are going to calculate it now. So this is the variable resistance we are going to find out for the thermistor. At everything it should be in a 0. When we are pressing the battery and the galvanometer, it shows the maximum deflection. When I varying the resistance value, which is I am pressing the 1000, when I am fixing the 1000, when I press it, the galvanometer shows the deflection on the right side. When I make it change to 2000, it goes to the maximum to the right side. Making to 0 to the 1000 value and varying the 100 resistance. So example, if I place a 900, it shows the null deflection. So and then vary the ones value, tens value and all, it shows the null deflection. At 300, at 30 value, it shows the, at 20 value, it shows the null deflection. So we can write it would be 920 into 1, so 921. So that is the room temperature resistance value. For variable temperatures, we can find the resistance. Similarly, for example, at room temperature, we have find out the value by varying the temperatures. From the hot water, we are reducing the temperature. So by varying the temperatures, we have taken the R value by changing the resistances. And we find the ln R, so that is from R we are finding the ln R value, and 1 by T, that is Kelvin inverse. So Kelvin temperature we have to take the inverse. So 1 by 300 we can calculate it, so it will come 3.333. So for all the values the power comes 10 to the power minus 3. So we have put in the top of the column of 1 by T, and then we plot a graph between the ln R and 1 by T. By using these values of ln R and 1 by T, we plot a graph between the ln R and 1 by T. We will get a straight line like this. From that straight line, we can plot a slope wherever, not to the point to point, wherever we can draw a slope. And when we draw a slope, dy by dx, I have taken a 5.9 and 5.908 into 10 to the power 3 because of 1 by T into 10 to the power minus 3. We will get a slope value as 3500. This is the calculation for finding the band gap. Eg is equal to 2k into dy by dx. So k is a Boltzmann constant 1.38 into 10 to the power minus 3 joule per Kelvin, and dy by dx value is 3500. When I substituted 2 into 1.38 into 10 to the power minus 3 into 3500, we will get 9600 into 10 to the power minus 23 in terms of joule. So in terms of electron volt, we have to convert it. So this value is divided by 1.6 into 10 to the power minus 19. We will get 0.603 electron volt. So this is the band gap of the intrinsic semiconductor.